This week we're looking at surds, which are a type of irrational number. So surds are numbers written with a square root. Root 3 and root 271 are example of surds, but not all numbers with a square root sign are going to be irrational numbers. We'll see that sometimes we can use a square root symbol and end up with a number which is rational. That means it's a number that we could write as a fraction or as an integer, as a whole number. Here's a few examples to have a look at. Now, one thing to watch out for, the square root symbol means the positive square root of something. You'll remember that if we were told, say, x squared equals 36, when we're solving and we square root both sides, we would say that x is plus or minus the square root of 36, so x is plus or minus 6. The reason we need the plus or minus sign there is because the square root symbol on its own just means the positive square root. So here, square root of 36, the positive square root of 36, that's just equal to 6. That one is not irrational because it's an integer. Let's have a look at some others. Here's one. I'm spotting square numbers here. The square root of 4 is just 2 and the square root of 9 is 3. So the square root of 4/9 is 2/3. Again, that's rational. We've got a few examples here where we've got a square root of a number multiplied by itself, either written as the number multiplied by itself, like root 7 times root 7, or with a squared sign, which does just mean that number multiplied by itself. You can check this with your calculator, but the number square root of 7 times itself, well, square rooting and squaring are opposites, so root 7 times root 7 is just 7. Root 11 times itself, 11. Root 15 times itself, 15. What about this one? 6 1/4. Well, 6 whole ones would be 24 quarters, add the 1, so that would be 25 quarters, and we want the square root of that. So the square root of 25 is 5, and the square root of 4 is 2. So 5/2, or 2.5. Rational again. Square root of 196. Now, it's a good idea before your GCSEs to try and learn the square numbers up to 20 squared is 400. If you've done that, you would know that 196 is 14 squared. So the square root of 196 is 14. And here we've got root 3/2 squared. Well, the numerator there, root 3 times itself is 3, and in the denominator we've got 2 times itself, 4, 3/4. So in fact, none of the numbers on this screen are numbers that we would call surds. So although they were all written with square root symbols, when we evaluate them, we've always ended up with a rational number. So these are rational, these are not surds. Surds are irrational numbers which do have a square root in. Pause the video and have a look at these calculations. You should have found that these two generalisations are in fact both true. It's not very easy to prove it, but we can just show with some examples. For example, let's say A is 4 and B is 9. So we'd have 4 times 9, which is 36 on the left, square rooted, and on the right we'd have the square root of 4 times the square root of 9. So the square root of 4 would be 2, and the square root of 9 would be 3, so the square root of 36 is 2 times 3, which is 6. That one is true. You'd get the same thing with dividing if we took this time A to be 36 and B to be 9 again, then square root of 36 divided by 9 on the left is the square root of 4, and on the right we'd have the square root of 36 divided by the square root of 9, which is 6 divided by 3, and the square root of 4 is 2, which is indeed 6 divided by 3, so that is true. Now, this is a particularly useful property when we want to simplify surds. Just like when you simplify fractions, you want to write the fractions with the smallest numbers possible, it's the same idea with surds. Instead of writing root 50, we'd rather put 5 times root 2, so we're using smaller numbers. Now, the idea of what we do here is we're looking for a square number, in this case 25, that goes into the original number. So 50 is 25 times 2. The square number, well, we can do the square root of 25 and we get 5. The other number that's not a square number, we can't simplify that, so we've just got 5 times root 2, and as with any algebra we miss out the times sign, so we get 5 root 2. Pause the video and have a go at these 4. Okay, so root 75, well, that's got a multiple of 25 again, so that's root 25 times root 3, because 25 times 3 is 75. But root 25 is 5, so we just end up with 5 root 3. Let's have a look at root 27. Now, what's a square number that goes into 27? Well, 9 goes into 27, so root 9 times root 3 is root 27, but 9 square rooted is 3, and then we can't simplify the root 3. What about root 98? What square number goes into 98? Well, think of your square numbers. 1 goes into anything, but we've got 4, 9, 16, 25, 36, 49. Aha, 49. So 49 times 2 is 98. So root 49 times root 2 is root 98. So root 49 is 7, and then we can't simplify the root 2, so we end up with 7 root 2. And finally, 63 is 9 times 7, where 9 is a square number. So root 9 is 3, we end up with 3 root 7. This is how we simplify surds. We look for a square number that goes into the original number, rewrite the original number as a product of the square number and something else, and then do the square root to end up with an integer multiplied by a surd. Use a calculator to check out these. Pause the video. So you'll have found that root 2 plus root 3 does not give you the same value as root 5, and root 8 minus root 3 does not give you root 5. So we can't just kind of ignore the square roots and add up the numbers. So those top two don't work. What we can do though is treat the square root a bit like a letter in algebra. If we had 6x take away x, we would have 5x. This is where I'm saying root 3 is like x. So this one also, that wasn't true. So you can't just kind of cancel off those root 3's. But finally this one, if this time we said, well, let's call it y now, if root 2 was the y, if we had 5y add 2y, then we should have 7y. And you'll find 5 root 2 plus 2 root 2 does give you 7 root 2. So that was the only calculation there that was correct. This is an important thing to learn, that you can't just add and subtract surds in the way that we can multiply and divide. If you remember from before, root 2 times root 3 is the same as root 6, but root 2 plus root 3 is not the same as root 5. Pause the video and have a go at these. So Whitney's used that rule that we just said we can't use. 75 take away 27 is 48, but we can't just ignore those square roots, so that is not true. What we can do though is simplify by taking out square numbers. So 75 is 25 times 3, so that will give us 5 root 3. 27 is 9 times 3, so that will give us 3 root 3. And then 5 of something minus 3 of the same thing leaves us with 2 of that thing. So Amir was correct. Another thing that we do to simplify surds is to avoid having a surd in the denominator of a fraction. So what we want to do is called rationalising. To rationalise means to turn into a rational number on the denominator. So rationalising a surd, we use this thing that looks like a bit of a trick, but you'll see how it works out. If we've got a root 3 in the denominator, if we were to multiply that by root 3 times root 3 would give us 3. So that would seem sensible, but we can't just go and do something on the denominator without doing the same in the numerator. So we'd have to do the same on the top. So 5 times root 3, well, that's just 5 times root 3. So the numerator is just 5 root 3. We can't simplify that. But the denominator now, 2 times 3 is 6. That's a rational number, and that's what we wanted to do. We have rationalised the fraction 5 over 2 root 3 to give us 5 root 3 over 6. This is usually considered the simpler form when you have the surd in the numerator rather than in the denominator. Here's some more examples of rationalising denominators. So in this first example, we've got a root 7 in the denominator, so we don't want that. What we can do to get rid of it is to multiply by root 7. But we'll have to do the same thing on the top as well there. So on the top we've got 3 times root 7, which is 3 root 7, and on the bottom we've got 4 times root 7 times root 7, so 4 times 7, which is 28. So we end up with 3 root 7 over 28. Here's another one, 2 root 5 over 7 root 3. Now there's two surds there, but the one that we're interested in is the one in the denominator. So to get rid of that root 3 in the denominator, we need to multiply by root 3 in the denominator. So 2 root 5 times root 3 is going to be 2 root 15, and then 7 times root 3 times root 3 will be 7 times 3. So that's 2 root 15 over 21. The last thing to look at is multiplying out pairs of brackets or expanding brackets. We use the FOIL method, so first, outside, inside, last, in the same way that we do when we're multiplying out things like if it was 3 plus x and 5 minus x, for example. So let's have a look. First terms, 3 times 5 is 15. Outside terms, 3 times minus root 2 is minus 3 root 2. Inside terms, root 2 times 5, that's 5 root 2. And the last terms, root 2 times minus root 2, well that's minus, and then root 2 times itself, that gives us 2. Now we can collect like terms here, as in integers. 15 minus 2 is 13. And then the root 2 terms, we've got minus 3 of them, add 5 of them, That will give us plus 2 root 2. Let's have a look at the next question. So this time we have got 7 times 6, first of all. So first term, 7 times 6 is 42. And then the outside term, 7 times minus 2 root 3. Well, 7 times minus 2, that would be minus 14. So that's minus 14 root 3. Inside terms, 4 root 3 times 6. So 4 sixes are 24, and that's multiplied by root 3. And finally, the last terms, 4 root 3 times minus 2 root 3. Well, we've got a minus there. 4 times 2 is 8, and root 3 times root 3 is 3. So we've got 8 times 3, that's 24. Okay, so 42, take away 24, that will be 18. And then minus 14 plus 24, that will be plus 10, and that's how many root 3s we've got. So our final answer is 18 plus 10 root 3.